Hello everyone, today we're going to be talking about mass spectrometry, which is an analytical technique we use in organic chemistry. Now, mass spectrometry is where we take a gaseous sample and we bombard this sample with a stream of high-speed electrons, which acts to knock an electron out of the outer shell of the molecule. This forms a positive ion. Now, heavier positive ions will take longer to reach the detector than lighter positive ions, and that's how we can work out this along the x-axis, which is the mass to charge ratio. Now, it's worth thinking that the mass to charge ratio is essentially the mass divided by the charge. Now, I've just said that the charge is +1 for all the ions. So in actual fact, the numbers along the bottom correspond directly to the mass of the ion, because anything divided by 1 is itself. So it is very important if you're asked to label up a mass spectrum in the exam to remember that it's mass to charge, or m divided by z, not mass along the bottom. And up the side we have the percentage intensity, how much of that sample was detected. And the first thing to mention with a mass spectrum is the peak that is furthest to the right. Now, a lot of you will be watching and saying, well, actually, he's missed out this peak. This is furthest to the right. This peak is so small that we are going to ignore it for now. It is important, and we will come back to it later, but the first peak that we want to look at is the furthest to the right that is big. And this peak is called the molecular ion peak. And this gives us the MR of the sample molecule. So our sample, let's call it sample A, or compound A, we know has an MR of 46 from the molecular ion peak. And I'll just pop a purple dot here so that we know that's with that. So the peak that is furthest to the right on the spectrum, ignoring a tiny peak 1 unit of mass to charge after it, is the molecular ion peak, which corresponds to the MR of the sample. Moving along, we then have these peaks here. These are our fragment ions. So I mentioned at the start of the video that the molecules are bombarded with a stream of high-speed electrons. Sometimes these high-speed electrons actually fragment the molecule, they break it up. And fragment ions are a great way of working out what clusters of atoms are in your molecule. So let's take this first peak here. I'm going to highlight in this peachy colour. This has a mass to charge ratio of 15. So we've got a fragment ion with a mass to charge ratio of 15. Now, having a think about some common fragments in organic chemistry, we've got things like a methyl group, a CH3 group. We could have a carbonyl group. We could have an amine group. There are plenty that we can have. We can even have a phenol group as we advance. There are plenty of fragment ions that we can have. Now, don't forget these are ions. They all have a positive charge. So there's plenty that we can have. And using our periodic table, we should be able to work out that something with a mass to charge ratio of 15 is more than likely going to be a CH3 group. Carbon has an AR of 12, hydrogen 1, so that's 12 plus 3 lots of 1, which is 15. So to recap, from our purple peak, we got that the compound must have an MR of 46, that's the molecular ion peak. From our peachy pink peak, try saying that fast, we have that a fragment ion within the compound A must be a methyl group. And now we're going to have a look at the next peak, peak, which I'm going to highlight in yellow. Here we are. There's one with 17. So this has a mass to charge ratio of 17. Now currently I'm not sure what 17 is. So I'm going to have a little think. I'm going to look at my periodic table and I can see that oxygen is 16 and we know that hydrogen is 1. So perhaps this is a hydroxyl fragment. Don't forget these are all positive ions. And so we'll have a look at our final fragment ion here, which I'm going to highlight in blue. And this one has a mass to charge ratio or MZ of 29. Now 29, that's quite big, so we might have more than 2 carbons in it. I'm thinking, looking at my periodic table, this might be a CH3 group, then with a CH2 group on it. Let's just count that up. Carbon is 12, add 3 is 15, add 12 is 27, add 2 is 29. So I think that our blue peak is going to be a CH3 group followed by a CH2 group. And again, that's a positive ion. Now, you may be thinking, why is the CH3 fragment ion at 100% intensity? Well, what the computer does when it creates the mass spectrum is it takes all of the fragment ions and it sets the most abundant fragment ion to 100% and then everything else in ratio to it. So the most common and abundant fragment ion is the CH3 group. So currently what we have is a molecule, compound A, which has an MR of 46. We know it has a CH3 group in it, a methyl group. We're actually led to believe it's got an ethyl group in it, and it has an OH group. So it's more than likely that we're going to have an ethyl group, which is CH3CH2. Now if we draw out the full structural formula of this ethyl group, we're going to find out that actually we've got our CH3 and our CH2. Carbon is 4-valent, it can only form 4 single covalent bonds, so carbon only has the option to form 1 more bond. Now we know that we've ticked off that we've got a methyl group, we've ticked off that we've got an ethyl group, we're still missing this OH group, which would sit nicely on there. So that's all our fragment ions included in our molecule. Let's very quickly count this up and see if this agrees with our MR of 46. So we've got 1, 2, 3 hydrogens, that's 3, plus 12 for a carbon is 15, 12 for another carbon is 27, 2 on the hydrogens is 29, plus 16 takes us to 45, and plus 1 takes us to 46, which agrees with our molecular ion peak. So we can say that compound A has the formula CH3, CH2, OH, which is, as you will recognise, ethanol. And if you're not quite sure where I've got the name ethanol from, then do check out our video on naming alcohols. That's how we use a mass spectrum to be able to identify a compound. And there's one final thing before we go. It's this peak here, the tiny little peak after the molecular ion peak. Now, in an exam, it has been a multiple choice question before to explain what this peak is. Well, it's the molecule, it's compound A, with 1 atom of carbon-13 included. That's all it is. It's just carbon-13, which is a different isotope, and that's it. That's how you interpret a mass spectrum to get an identification of a compound. Now, chances are in the exam, you'll be asked to relate your mass spectrum to an infrared spectrum as well, so do feel free to check out our other video on how to interpret infrared spectra. Thank you.